Okay, so the video that I messed up, I'm going to kind of pick up from, but I'm also going to quickly recap. So this kind of functions as a standalone video, hopefully. So what I've done, I'm just going to walk through here a little bit. I've declared my S and E. These are my values, right? X-axis, Y-axis, and then K, which I needed an equation, is just the length of those vectors, right? They have to be the same. Then I went ahead and created the S times E and the S squared vectors. That just kind of simplifies my life later when I start doing the calculations. Then any of these that are XS is the sum of S, right? XSE is the sum of that SE vector and so on, which helps abbreviate the coming equation so that I don't have to write sum parentheses a whole bunch of times. Then I do my calculation of A and B here. These equations are just pulled directly from the notes, or you could pull them directly from really any example, I'm sure. They're pretty common. Okay, so I think that's where I left off because then I tried to plot some things and it didn't work out so well. So the thing that I tried to plot first off is I wanted to use a scatter plot to show the measured values. Okay, so that's what's popping up here. And you can see they're not really quite a straight line that you would maybe want. That would be an ideal transfer function for this, right? But what I can do is I can overlay that with a plot of this P, which I'm just calling P is the equation for the A and B that I calculated. So if I do that, it totally did not work. Okay. Oh, it's because I didn't hit enter. Okay, there you go. So you can see that linear estimator is doing a pretty good job following the curve. Okay, so now what I need to do is go ahead and find the sensitivity. Now, what the sensitivity is defined as in this case, right, is the change in output by the change in input. Sorry, in all cases. In this case, that's the sensitivity. Cool, it's spelled right, is the change in voltage by the change in pressure, right? Out over in, voltage output, pressure input. The other way of saying that, though, is because I have the equation. If you look at the plot, this plot is described, the x-axis is the change in pressure for you guys, and the y-axis is the change in voltage. So my example, I don't have the units popped out because it's kind of generic numbers. It's not the same as your example, but what's convenient and is the same example is B is your sensitivity, because that's what the units of the slope have to be in order for it to make sense. Okay, so then the next thing, I guess I'll add a little bit of note here actually, so you guys can follow along, right? Comments mean notes. All right, the next thing that you can do is find the error. Now there's really two types of error, right? So the first error is the error due to the estimation. Due to find that, I want to use the worst case, difference, right? What is my maximum difference that I test? And to really do that, I would need to go and measure it a bunch of times to make sure I'm accounting for all the noise. But in this single run test, an easy way of finding that in Python is use this command, which is maxval maxlog is equal to the max of the difference between P, that equation that I wrote up here, and E, right? So this is really just the difference between the measured and the actual, or measured and predicted, I guess is a better way of saying that. But for the noise, I don't really want to include the estimation error into this. So I'm going to find the location, right? Really, I could pick any location along P and call P my reality. But what I want to do is I actually want to measure it as close as possible. So I'm going to go ahead and do the same thing with min and find the minimum location and value. So if I do that same expression, you can see that min val comes up with the 0.06 and the minimum location is 7. So that means S at 7 is a small error, which, okay, that's fine. Okay, now that I can do that, I need to define what I mean by, well, signal and what I mean by noise, right? So the signal that I'm interested in is this, where the V ideal, or I guess I could say V expected, because it may not be the ideal compared to like a data sheet or something, but I'm going to stick with it, where I'm just using the A and B again, and then I use S at its minimum location, because that's where I want it to be. So that's going to pop out this value of 19.264. And then I need to have the noisy signal for a comparison, which I'm just going to pull there. Now, this is where I think you guys are going to get confused. It's that same equation, and I'm choosing the same location, right? So this is still going to be a pressure value for you guys. But mine is just this kind of generic S, unitless, whatever, and I'm going to add some VN to it. Okay, I haven't defined a VN, so I'm going to go ahead and delete this before I enter that in. Let's go ahead and define my noise. Your guys is like 300 Pascal or something. Mine's going to be 0.7 mystery units. So now I can go ahead and go back to that V noisy estimation that I was talking about. Sorry, I'm copying and pasting this so I don't have to type forever for you guys. Okay, so now V noisy is A plus what it should, sorry, A plus B times what it should be plus the noise, right? In your case, noise is pressure, mine's not. Now I can find the error that results from that noise. There we go. So the noise error, and I keep messing up this in class because I'm really scatterbrained this semester apparently, but what you want to do is subtract the difference between the measured and the expected divided by the expected, because we're always going to do it proportional to what we expect, which makes more sense. I know I screwed up the example in class, but this is the real one that we really want. So expected, the difference between the expected and measured divided by expected. Okay, so I can remove the semicolon because that expresses the output, and it looks like I end up with a 10% error due to a 0.7 VN. Now, theoretically, I could go ahead and change VN, right? And we should see something like if I do roughly half of that, I guess exactly half of that, and I have this new VN, then I can rerun this noisy equation and then pop up the noise error, which is now 0.5, right? Which is expected. It should be half of whatever this is. If I want it as a percent, I just take noise error times it by 100, and now I have my percent error. Okay, that's all that walks you through finding the sensitivity and finding the error. So I hope that answers most of your questions. If you're still stuck on the homework, go ahead and email me.